Welcome to my presentation. Okay, here. Okay. Hello everyone. I'm Eugene Wang, the corresponding author for the research time travel LLM-assisted semantic behavior localization with Git Bisect. Today I'm presenting for the work. This is the work I've done along with my joint author Wizzy Han on using LLM to assist Git Bisect for faster error localization, submitted under Part 1 of Track 1 Tools and Platform for supporting scalability at IEEE SCALCOM 2025. So basically, Git Bisect is a built-in debugging tool that works incredibly well. You start from a well-known commit and a known bad commit. Then Bisect repeatedly checks if there's a midpoint until the first bad commit. This is extremely useful in large projects because instead of manually combing through hundreds of thousands of commits, we can just narrow it down to a few culprits very quickly. But this figure shows that the process visually, we begin at a good starting node and a bad ending node. The algorithm automatically splits the history, check the midpoints. If the midpoint is good, the search continues forward. If it's bad, it moves backward. Eventually, it converges on a single node, which is the third run right in the graph. The exact commit that introduced the regression. The comments are on the right. It's basically git bisect start starts the process. If you find a good node, do git bisect good. If you find a bad node, just do git bisect bad. Only 3 commits that drives the entire process. But git bisect is very broken for a very large scale repository. So for classic git bisect, it only works under a very big assumption that every test result is deterministic, meaning that each commit is either good or bad with no ambiguity. In reality, large-scale systems rarely behave that cleanly. We face flaky tests where the same commit can pass or fail inconsistently. We also see non-monotonic regressions, where a later commit might introduce a fix to an earlier failure, so the pattern isn't strictly good to bad. Additionally, upstream divergence or dependency changes outside our control can introduce noise into the process. This diagram highlights this. Commit A and B are clean and good. Commit D and F are clearly bad. But commit C and E are flaky, giving us inconsistent signals. This makes traditional bisecting unreliable at scale because it breaks down as soon as you leave the near and binary world and steps into the messy real world. So, case in point, this is a screenshot from Chromium's Lucy test infrastructure. The test tab strip browser test shift tab preview shift between groups is marked as flaky because it doesn't fail consistently, as you can see in the test variants. Sometimes it fails, sometimes it passes. The infrastructure records the failure, but because it's non-deterministic, bisecting towards this failure can yield misleading results under monotonic assumptions. This shows that flaky test breaks the binary assumption behind classic Git bisect. In large projects such as Chromium, with thousands of tests across multiple platforms, these kinds of flaky tests are very common. One more challenge is semantic changing behavior. So not every regression can introduce a hard-coded coding failure. Sometimes the change is behavioral, but because of the interdependencies and upstream downstream effects, it somehow breaks the code later down in the line. So it could be a behavior change that's good, leads to misleading signals, or introduce noisy signal that leads to a breaking down the line. But the down the line change isn't code breaking. Just like we saw in the Chromium example, here's an example where the test passes on retries, but when the developers try to use it, the dialog, the click just doesn't register because the behavior has changed. And if we zoom in, this is the logs from the Chromium test run. We notice how many tries are being executed, but we have mixed results. The on my activity link click are clearly not registered due to behavior change, which is due to very noisy reasons. This button could be like not registered in time, or it could be a JavaScript not being loaded in time, or it could be an upstream change, which resulted in a library needs to be imported, which results in the more time taken to import a JavaScript library. So many of these very introduce ambiguous results. And at scale, when you're running thousands of tests across massive code bases, this ambiguity slows everything down to the point that you just can't quickly identify a single point of failure. So to sum up, large repos means more commits, more possible breakpoints. Flakiness means more unreliable signals, and ambiguity means wasted time and effort. This is why traditional bisectors simply don't work at scale. So the core problem is to identify the first commit that introduces a regression under noisy condition. We must handle non-monotonic outcomes, for example, sequence of good, bad, good that breaks traditional bisect assumption. The process should run with minimal developer intervention and success. We define success by the following metrics: correctness, accurately locating the regression; robustness to noise, tolerating flakiness and inconsistent signals; and then efficiency, which is time and scale. Our approach is to use an LLM and augmented bisect with structural reasoning. So here's the overall structure of our LLM bisect process. We augment the LLM execution trace at each probe. The LLM follows the structural reasoning template, inputs, observation, hypothesis, verdicts for commits by commit judgment. Each probe emits a tri-state result, good, bad, or intermittent. A decision engine updates bounds, applies fallbacks, retry with replication or alternate seeds with intermittent, use evidence weighting across repeated probes to break ties. Allow non-monotonic sequences by tracking confidence bands, not a single binary line. Loop until we find the first bad commit with confidence and a short explanation with trace snippets and rationale. So to enforce deterministic results, we choose function calling as communication protocols. It converts non-deterministic predictions outputs into deterministic data. Instead of the model giving us free-form text, we force it into strict schemas. That one can be recognized and used directly by user-defined functions, which means no ambiguity. Every field is exactly as we expected. And then the LLM can call extractor functions. The extractor function can identify, retrieve relevant information like code entities, logs, or commit metadata. The results are then fed back into the model, refined for its reasoning, as we mentioned earlier. Finally, the model is instructed to compute a final output based on these process results, ensuring workflow is consistent, reliable, aligned with our debugging pipeline. So this is the structure of our function calling template. I'm just going to walk through it very quickly. So at the very top, we have a capture problem, which we try to capture the errors in the search code. And then we extract entities, index symbols, and map relationship via a thing called call graph. For each commit, we identify changes with listed change entities, and then decides the relevance by judge commit relevance. Once we check out a commit, we test it robustly with run predicate, then record the outcome using mark bisect. The loop continues with next bisect ref, steadily narrowing down to the root cause. So here is the worker graph of the program, which works on extracting entities. It builds on the previous flow. Once the LLM retrieves the execution trace, the judgment process itself is not monolithic. Instead, we parallelize specific extractors. One worker focuses on entities, another focuses on relationships, another one focuses on value, and then all the workers dump their results in the queue, feedback into a custom aggregator, which merges and reduces and reconciles potential conflict signals. And then we incorporate a feedback loop, which reduces ambiguous and noise outcomes as it cycles back into the process for refinement. In order to improve accuracy, we benchmark both open source and proprietary LLMs for judgment quality. We ran QLoRA fine-tuning on DeepSeek Code v2 with 50,000 examples from prominent open source repos, but only with 30 annotated tests. Prompts are designed to stress diffs, traces, and set semantics for better reasoning. We have lightweight policies that keep cost and latency low in CI-like pipelines so that if developers wish to implement this, they can totally host it on-premise, as opposed to queuing a remote LLM, which is potentially a security risk. So I'm just going to quickly go through our evaluation metrics. So on the left, you can see the training losses for our QLoRA returns. There's this early spike at about 22.5 at step 6. That's typical of parameter efficient fine-tuning. newly initialized adapter layers are usable for unstable for a few steps. After that, loss fall steadily as the adapter adapts to objectives. Because our data set is relatively small, we intentionally kept epochs low to avoid overfitting. We did a sanity check with a very, very small model, distilled GPT-2 on the right. To confirm that it wasn't a pipeline bug, we repeated training with the smaller model, which confirms the same descent trajectory. Overall, the accuracy improved, but two categories remain weak, which are error handling, which is stays at 50%, and runtime safeguards at 25%. I'm sorry I didn't include the chart in my slides, but it's in my paper. Our hypothesis are that these patterns are sparse and decoupled from dominant diffs. Therefore, our training model was not as efficient in capturing that in the training data sets. So we also conducted an ad hoc developer study at a small company work team with 7 professional developers. Study used across overall A/B setup. Each developer worked with both vanilla Bisect and augmented Bisect. To avoid biases, no one bisected the same bug twice, so that each bug was tested under both conditions. The result is that developers reported an average gain of 45.6% time saved with the LLM augmented approach compared to the traditional classic Git bisect approach. Obviously, there are many limitations and risks. Incomplete models or misleading data, that's one. Over time, as your code base changes, your model may not reflect the latest stage of your code base. That's another one. If you don't have enough compute power, you may not be able to host it on your on-premise machine. That's another one. And just to overall try to host it on your own premise is also a security undertaking. So the system is designed to fit directly into existing workflow on a CLI level, just like a gate wrapper, but we can see that being used in the CI pipeline to gate long bisects to avoid runaway jobs, and then we can cache results across multiple pools that save costs, and or developers can just use that as a safeguard when merging or undertaking a new dependencies. So in conclusion, we have shown that LLM-assisted bisect makes regression localization practical, even in the presence of noise, flaky tests, and ambiguous signals. By combining operational design choices like occasion, we can, in the future, improve the results even more. Developers reported a 45% reduction in time. Overall, I think there are still challenges on making it more efficient and more correct.